Nak record ke? Tak payah record. Record ke? Tak payah.
Let me just see.
Asyik guna WhatsApp masih okey.
It's not online, right? Oh, live?
No.
Not yet. How he will sit?
Just left it down.
Oh, left the laptop here.
Yeah.
It's okay. We can because it's okay.
It's okay.
Put it aside here.
Belum share lagi tak? Let me.
This one is new one. This one is new one. Just okay. Yeah, now okay. Start. No, it's not full.
Kena dapat speaker bercakap. Speaker?
Okay. Yes. It's okay. I think okay. Because speaker can
It's okay.
just go. Ah? No.
No, lagi.
Oh, lagi. Oh,
Yeah.
Okay. Wait.
Okay.
Okay, and I cannot see you.
Cannot see. So,
Okay. Just little bit.
can you see the
Nah, yeah, it's okay. Now, okay. Now, oh. Okay. Oh, it's lagging.
It's lagging.
Wait. Now, okay, I think. But why it's lagging?
No, because you need to send data to YouTube and then YouTube will.
Okay.
Is it cuba
Just put still there.
I can see now. Can you try this? Okay.
Yeah. patut ikut mana?
Test S. Assalamualaikum and very good morning. Attention to everyone. Please make sure your phone in silent mode as our program will begin shortly. Thank you. Ladies and gentlemen, please allow me to read the agenda for today. We will begin our program with opening remarks. Then we will have invited speaker session 1 at maybe around 8:50 to 9:30. After that, we will have a short photo session here. Okay, then we will have a tea and coffee break outside Dewan Perdana. Then after tea break, we will start with presentation. For concurrent session 1, we will start at 10:30. Until 1 p.m. at Dewan Perdana 2 in here, while concurrent session 2 will be start at 10 a.m. at meeting room 1. Meeting room 1 just right at the first entrance on the right. Okay, then we will have lunch outside at Palm Hill Cafe near the lift area, and surau and toilet will be in this floor, just on the right side. After lunch, we will have invited speaker session 2 at 2 p.m. until 2:30 p.m. in here, Dewan Perdana 2. After that, we will start the next concurrent session 3 in here also, Dewan Perdana. Meanwhile, for academic and industry meeting, will be at meeting room 1. And also, we have concurrent session online conducted by Dr. Sofian. Then we will have tea break at 3:30 p.m. until 3:45 p.m. The last concurrent session 4 will be start at 3:45 until 4:45 p.m. at Dewan Perdana 2. And academic industry meeting will continue in the same room. And lastly, we will start our closing ceremony around 4:45 p.m. I would like to mention about the assembly area for emergency. It's called Taman Putra Perdana, and the pathway and emergency exit will be indicated, sign shown by the hotel. Thank you. Assalamualaikum and very good morning, ladies and gentlemen. We are delighted to welcome you to the first international conference on future trends in welding, joining and additive manufacturing 2023. I am Nurin, the host for today. I would like to greet the conference chair for WJAM 23, Associate Professor Dr. Farazila Yusof. Next, our invited speaker, Prof. Dr. Inyu Peter H.P. Manurong from University Teknologi Mara UiTM Shah Alam, and also Associate Professor IRTS Dr. Muhammad Riza bin Al-Kahari is from University Technical Malaysia Melaka UTM. And also we have invited speaker from LJMU Liverpool Morse University, Dr. Prof. James. Before we proceed, I would like to invite Mr. Fazil Jamaluddin to recite the doa. Please welcome Mr. Fazil.
Bismillahirrahmanirrahim. Ya Allah, Ya Rahim, praise be to Allah, the Lord of the world. Peace and blessings upon our Prophet Muhammad sallallahu alaihi wasallam and his companions, and for those who follow his example till the Judgment Day. Allahumma Ya Allah, on this blessed morning, in conjunction with the first International Conference on Future Trends in Welding, Joining and Additive Manufacturing 2023, we seek you and grateful towards you in favor of all the infinite blessings to us, your humble servants, to live in safe and prosperous life. We seek your blessing for flawless progress of this event from the beginning till the end. We seek your guidance to steer clear of events that would be detrimental to the progress of this event. Ya Mujib al-Barakat, bestow peace to our beloved country Malaysia, reverse us from any threat and disaster, neither man-made nor natural disaster. And to you, Allah, we seek for security and prosperity upon us, our leaders in our country. Bestow patience in us in order to face challenges from you. Please accept our deeds and please reward us accordingly. Rabbana alaika tawakkalna wa ilaika anabna wa ilaika al-masir. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzaban nar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wasallam. Alhamdulillahi rabbil alamin.
Amin, amin, ya Rabbal Alamin. Ladies and gentlemen, this conference aims to enhance mutual collaboration for higher research level and activity in field of welding, joining and additive manufacturing. Despite the time constraint, we can gather a significant number of academicians, researchers and scholars in welding, joining and additive manufacturing to exchange and share their experience and research findings. Without further ado, I would like to invite Associate Professor Dr. Farazila Yusof to give an opening remarks. Please welcome Dr. Farah.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. A very good morning to everyone. Right. First of all, I would like to thank to those who are coming today. I can see my friends from various universities, from UiTM, UTM, from USM, SETI, MASA, and which one I didn't mention. Thank you very much for supporting this first conference for International Conference on Future Trends in Welding, Joinings and Additive Manufacturing. Right. So we aim that this kind of gathering to be done every year. Okay, the aim is not only to have presentations in academic, but then my aim is actually to have collaborations between the institutions and also with the industry. Right. So this is the first step. We have meeting in this afternoon to strategize how we want to move forward in this area. Okay, because as you know, especially in additive manufacturing, it's become more and more important in the current industrial practice. Right. I also would like to welcome those who are in online. We have a session not only physical here, but also we have the online sessions. We have invited speakers from Liverpool John Moore University. He will deliver the speech in the afternoon for the online session. We have a parallel, meaning that we have the physical and also online. And also we are streaming our event. So later on you can have a look for the invited speaker in the YouTube. Right? I think that's all for the welcoming remark. Hope this event is a first step to us to work together in this area. Thank you very much.
Thank you, Dr. Farah, for the opening remarks. Okay, ladies and gentlemen, now we move to the invited speaker session by Prof. Dr. Ing Yupiter Manurong with the topic of manufacturing simulation for fundamental and applied research. And a little bit about Prof. Yupiter is Prof. Yupiter is a full professor at School of Mechanical Engineering in University Technology Mara, UiTM Shah Alam, and former director of Smart Manufacturing Research Institute (SMRI), and also a leader of Research Interest Group at Advanced Manufacturing Technology. Without further ado, please welcome Prof. Vivita.
Pointer tak? Thank you very much, MC and also organizer Dr. Farah. I'm very delighted to be here to give speech in front of experts from manufacturing and also the future expert of manufacturing, our students, of course. Yeah. Today I would like to present a simple topic actually. Yeah. So I hope that at the end of these presentations we can do something. So the title is Manufacturing Simulation for Fundamental and Applied Research. My name is Jupiter. I'm from UITM. Former director, not director of SMRI anymore, no more. Yeah, so the former director of Smart Manufacturing Research Institute. All right, the outline. I have actually 60 pages. Yeah, I have to go a little bit faster. So a little bit introduction, and behind the outlines here, yeah, I have put some notes. Yeah. On the introductions, we would like to see what are the current challenges yeah, of the virtual manufacturing or manufacturing simulations currently. And then I would like also to present on these case studies, yeah, some case studies from others, yeah, from past researchers, which inspired, motivate us, our team, yeah, our group, to do more and deeper on this manufacturing simulation. The question is, can we do better? Yeah. Or if not, then let us collaborate. And then in the third part, I would like to introduce a little bit on the selected case studies. Yeah, it's actually done by our students here, yeah, postgraduate students. Yeah. I'm also bringing some askar, yeah, daripada SMRI. Yeah. So these are actually their research. Yeah. So don't ask me kalau tanya ada equations nanti dan yeah, refer to them. Yeah. So and then yeah, this is like our journey. Yeah. So you will see then where we started. Yeah, and then what we are going to do actually in the next. I will end up with the conclusions and also further research. Yeah, can be considered as like our dreams. Yeah. So which direction we would like to go? Yeah, our group. All right, and as the introductions a little bit, yeah. So manufacturing simulations, if you go to Europe or Switzerland, yeah, or German-speaking countries, yeah, sometimes they are referring to the virtual manufacturing, yeah. So also not virtual manufacturing. There are a lot of definitions on that, yeah. So since many years, yeah, the term as the next revolutions in the global manufacturing, yeah. And there are a lot of definitions on the virtual manufacturing or manufacturing simulations. I don't want to go part by part here. Yeah? But the most important thing is this virtual manufacturing, the fundamental concept, yeah, is the notions of the manufacturing before manufacturing, yeah, with physics-based, yeah, data-driven from the experiments and so on and so forth. Yeah? Some things we have to know also, yeah, before we go deeper into the manufacturing simulations, that simulations will never replace the experiment, yeah? But it can minimize, yeah, the number of the experiments, yeah? Hence it can reduce the cost. And the simulations results are never 100% correct, yeah, because of these points actually. Yeah? The input data is the approximated,
mathematical and geometrical model is idealized, and the accuracy is also limited, yeah, by the computer. Yeah, we have got some problem last week that some software cannot be installed, cannot be run, yeah, can be installed but cannot be run in a certain computer. Yeah, so it means that it depends also on computer. Yeah. Before we go deeper, yeah, I would like to see here that one is I think from Kordiban. Is one of the expert, yeah, researcher, yeah, from UK, I think. Yeah. So what he said is actually this one is very interesting. Eh? Nobody trusts a computer simulations except the guy who did it, and everybody trusts experimental data except the guy who did it. Why not combine the two and get results everybody can mistrust a little? Yeah. That one is a very good site from Kordiban. Yeah. And then we can compare also here. Yeah? We can see. Why the simulations can give some advantages. Yeah? For example, here is cheaper, yeah, faster, parallelizations is possible, yeah, and also multiple uses. If you compare with the experiment, yeah, so this one is costly, yeah, slow, yeah, sequential, and sometimes you can use only once. Yeah. So the challenging. So there are conflicting objectives, yeah, in the manufacturing simulations. Yeah. So we would like to have here fast calculation. Yeah. So we would like to have process change. Yeah. For example, if you do a coupling process, yeah, you would like also to do the couple simulations on that. We would like to have the real physics. Yeah. So that it will represent all of the experimental activities, yeah, or cases, and also we would like to have the simplifications on that. Yeah. So this is like the conflicting objective. Yeah, if we are using the manufacturing simulations. So how to resolve this one? Yeah, so we need the interdisciplinary sciences. Yeah. Between some maybe members, yeah, within the groups, yeah. Not always other faculties actually, yeah. So maybe the members in the group, yeah, we can specialize on a lot of some interdisciplinary sciences, yeah. And then the applications of simulations is often only a single process, yeah. But the directions is the chain process. Yes. Nowadays, currently, yeah, how we can simulate the process, yeah, after one process. Yeah. So, for example, if you are doing the forming and welding, for example, or warm and forming, yeah. So you need also the simulations, the couple process of the simulations. It means that all of the data, yeah, from the previous process, yeah, you have to transfer. Yeah. It cannot be the single process. So we would like to have the faster simulations. Yeah. So this one, yeah, there are some methods on that. Yeah, I would like to introduce later on. Yeah, how we can do the faster simulations results. Yeah, to get the faster results on that. Yeah. And then nowadays, yeah, the deeper simulations, yeah, call it deeper simulations, so that the people are trying to see in the microstructural level, yeah, on the simulations, not only on the meso or macro level. All right, this is the existing simulations fields in the research. Yeah, we have actually. Nowadays, yeah, we have continuum theories here, yeah, and also the discrete dislocations dynamics. Yeah. For manufacturing, normally we are moving in these fields. Yeah. So you see here, yeah, this one in the scale meter and millimeter. Yeah. So here, yeah, normally it's done by the faculty of the physics, for example. Yeah. So in manufacturing, the industry, for example, yeah, so there are maybe they would like to have more in this, yeah. R&D maybe, yeah, we move to this, yeah. If you see here, yeah, the crystal plasticity is nowadays, yeah, they are also moving towards this direction. So I would like also to show here, yeah, this one is I think the statistician, yeah, of Box, yeah. So he said that essentially all models are wrong, yeah, but some are useful. All right, with regard to the manufacturing, for example, yeah, here, yeah, so we can say that we can divide into two, applied and also here fundamental. Yeah. So if you see here the continuum finite element, yeah, we can have some methods here. Yeah. For example, thermal, yeah, mechanical, thermomechanical. Yeah. This is considered as the applied. Applied research. Yeah. So here is for the fundamental. Yeah. So we are doing this kind of the discrete dislocations dynamic. Yeah. By having the crystal plasticity finite element and also cellular automata. Yeah. Phase field. Yeah. This one is more to the fundamental. Yeah. In between. Yeah. In between. Yeah. Between applied and fundamental. Yeah, we can do this kind of the thermomechanical metallurgical and also thermomechanical fluid. There's combinations between CFD and also continuum mechanics, solid mechanics. So here the objective, you can see, the objective, yeah, what we can do, yeah, for having, for example, only the temperature, yeah, distortions, yeah, and so on and so forth, yeah, up to the grain structure and texture. In terms of the manufacturing simulation itself, yeah, so we differentiate into macro, yeah, meso, and micro. Yeah. So you see here, yeah, so the user, yeah. So the macro, yeah, normally the industry would like to have faster simulations result. Yeah. So they would like to have this macro scale. And here, yeah, meso, yeah, we call it also as the thermomechanical method. Yeah. This one is actually between R&D and industry. Yeah. And in the micro, yeah, this is more to the R&D. Yeah. If you see also here, yeah, the computational time, yeah, it's very short. Yeah, the industry would love to have this kind of simulation method. Yeah. And here, yeah, a little bit short. Yeah. And here is very long. And level of detail also, yeah, you can see also, yeah, very low, yeah, low and high. Yeah. And the quality of result, yeah, sufficient, good, and very good. If you see here, yeah, lumping is one of the methods which we are also investigating until now. What is that actually? So if you see here, we differentiate between non-lumping. This one is very slow, right? So it means that you can imagine if you have big components, yeah, and then you have to do that kind of the simulations, yeah. So it will take a lot of time. So what we can do is actually, yeah, we can do lumping here. Yeah, lumping meaning that in the lumping moving, yeah, it means that some elements, yeah, is combined together, yeah, so that it is a little bit faster than this non-lumping one. And then here is lumping layering. Yeah, some software is using this lumping layering, yeah, for example SLM. Yeah, so it will use the equivalent heat source equations here. Yeah, so it means that layer by layer, the whole layer, yeah, will be simulated. Yeah, will be lumped. We call it. So challenges in the macro here, yeah, and in the meso. Yeah. So for macro or inherent strength method, So the Japanese professors or researchers would love to do the ISF a lot. I saw a lot of journals, they are using the macro. But in macro, you need equations which you trust that it is correct. Or you need the calibrations for that. So for the meso or TMM, thermomechanical method here, you need also to know that the temperature is correct. So that you need also, you have to do the calibrations for the temperature. So dua ni, both you have to consider. So in the micro scale, it's different story. So ini kita tengok, we are looking at the grain boundaries and so on and so forth. So we are considering the crystal orientations here. The look is normal, and also the deformations. So this is also something new in the simulations world, especially for the manufacturing. A lot of forming process is coupling with this one. So meaning that meso and micro. So also with defects, for example, to find the damage and so on and so forth. The strain, stress, and so on and so forth. All right. So I go faster a little bit here. Some case study. So at Volkswagen, this one is from 2019. So this is the Mr. Ralf Sundermeyer. This is the director, the lighter of the CAD. So what he said is in 2025. That one is the 2019. So 2019, short before COVID. So I think that one will be extended. So 2025, he said that in Wolfsburg, Volkswagen, each engineer shall be CAE expert. So you can imagine that the employee maybe 40,000, the engineer maybe 2,000, 3,000, 4,000, 5,000. So in any computer, they have to have this CAE. This is their dream. So that the engineer must be capable to do this kind of CAE. So here also, Renault, for the Clio, small car, they develop the cars without physical prototype. So they trust the simulations or the trust of the simulation is there. So without any physical prototype, only the simulation. Here at Audi, I'm also dreaming until now that I can get call from Proton atau Perodua. So call me, you Peter, can you do that kind of investigations on the welding sequence, for example? So this is for Audi. What they are doing is here actually, they would like to define which welding sequence is appropriate for the door. So normally they are doing 80 experiments. With the help of the simulations, they are doing only 5 experiments. So it means that they will try by using the simulations, the sequence and so on and so forth, so that they will find the best sequence for laser welding of the door. This is for the laser brazing. Also, that one is I think Volkswagen. They simulate without holes, with holes, and the holes after the brazing. So meaning brazing first and then baru hole, then holes. Then they would like to see the distortion. So that kind of the projects is quite interesting. So this is also done by automotive industry in Germany. They are investigating the self-piercing rivet, and also by using simulations. You see here, so the normal SPR, they need 2085. With this new idea, they reduce only 277 pieces only. So you see the impact of that kind of the research. testing Porsche. Yeah, so they are using also simulations for the material testing. Yeah. What they said that you see here, yeah, the decrease of the development expenses and also development time. Yeah. So they are also moving towards the virtual test. Yeah. By the way, this one is done at WJAM. Yeah, simulating the tensile test of the sport welding. So this one is warm rolling. Yeah, it is almost similar with the Cranfield. Yeah, they are also using that kind of things. But what is interesting here, this one is with our partners also, yeah, from the German university. They would like to weld and then roll. Yeah, by using these simulations, they can define in after how many seconds I have to roll the plate after welding, so that I have the fully recrystallization. Yeah? So they found out, yeah, I think 4 or 5 seconds after the welding, they have to start rolling. Yeah? So that kind of thing they can we can simulate. Yeah? So here, yeah. So you cannot see, but somehow this is actually the result. So here also, yeah, they are simulating for the bipolar plate. Yeah. So in Germany, they start already with the steel for the bipolar plate, not graphite. Yeah. And you see here, yeah, 0.1 millimeter. Yeah. You can see here the distortions. Yeah, before they are doing they have done the proper simulations. Yeah, after proper simulations, yeah, you see here, yeah, bipolar plate of the steel. Ini pun menarik juga nih testing. So last time if we do the final element method, always here isotropy. Yeah, we never consider the anisotropy. Yeah, you see here the difference between this. Apa? It's different. Ini yang baru nih, the latest ya, from Milan brand, RMIT, self-heating. Yeah, no need self-heat treatment. Yeah, no need to do heat ataupun heat treatment in the oven. Self-heat treatment. Yeah. What they found is certain speed, they will move, the temperature will be located only on this temperature, critical temperature here. Yeah. So no need to do experimental first. Yeah. Kalau buat experimental first, yeah, then it will be costly. Yeah. So that here I think that one is 800 millimeter per minute. Yeah. It will produce the best ultrafine lamella alpha beta microstructure without heat treatment. By the way, they are using also Simufeng, sirkuit asal. Ini yang menarik lagi ya, wood. This one is from the Dresden University. Wood. Wood is very interesting, because from tree to tree, it's different. It's not like steel. Maybe steel is similar the properties from batch to batch. Yeah. Here from tree to tree is different. Yeah. So meaning that the properties of the material is every tree. You have to investigate. This one is from Daimler Chrysler, Mercedes-Benz. It's also doing wood. So this one is I would love also to start with this wood punya ni actually. Okay. So this one in terms of the generative design lah, yeah, generative design or topology optimizations. Yeah, this one is logo for Airbus. Yeah, and Honda. This one is BMW. Yeah. They're doing that kind of topology optimizations or generative design. Yeah. Here, ini juga, it's artist, Philip Stark, the first apa namanya, commercial chair by using design by using generative design. I hope also my student ada yang apa namanya ada seni-seni sikit, tapi mechanical engineering ni agak susah sikit on that. So that kind of thing we can apa namanya, we can check and then see the stress distributions and so on and so forth. Alright, so I don't have time. 5 minutes boleh? Alright. So that one is from our sideline. So ada beberapa selected case studies yang kita buat, which we have done at our institute. Yeah. So the first one, okay, some facilities dulu. So kita ada apa namanya, we have softwares, yeah, and also we have apa namanya, normal equipments lah. So for doing the experiments and so on and so forth. So here is our collaborations actually. Yeah. So mostly we are collaborating with German universities, yeah, and now we are moving to the Austria and also Switzerland. So kita tak ada, we don't have this one actually. Yeah. This one is from our partner lah. Yeah. Everybody knows 3D Gens. Yeah. Take the picture, put here. But here we have, yeah, and here also we don't have this one. Yeah. So this one also from our partner. Yeah. So this is the software we are using here for our research. Yeah. So here is open source. So jangan jadi don't think that the apa namanya yang costly software ni. Yeah. We can also use, for example, Damas. Anybody ada yang guna Damas? Open source, yeah, for the crystal plasticity. Ini no cost. Takut. Okay, ini kita punya journey tau. Yeah. Kita buat macro scale tadi saya cakap so we have to do the apa namanya calibrations. This calibration is very tedious. Yeah. This one is our first apa namanya try untuk calculate the distortions from SLM specimen here, yeah, by using macro scale, together with Cambridge also. So we found out the computational time is quite short, yeah, here, but the result is not good. Kenapa? Because these calibrations, you can see here, after you apa namanya, you print, you have to cut. You have to print the cantilever like this. You have to cut first the base plate, and then you have to cut also here, yeah, to see the deformation. That one is for the calibrations and not the distortions for the part here, yeah. Just for the calibrations, yeah, to define the strain and then put into the macro scale OISM. Yeah, the strain is used, is important. Yeah, very important. Fail, And then we move to this one. Yeah, bit on plate. Yeah, bit on plate. Yeah. Guna macro scale dengan meso scale. Yeah, ISM dengan TMM. Yeah, dua ni ISM, TMM. Yeah, we do by using robotic welding and so on and so forth. Yeah, so we found out here. You see also here. Yeah, this one is the apa namanya? What's it? Tak nampak dah. Computational time I think. Yeah, so computational time. Sorry, error. Error. Yeah, so error TMM nampak sini ya, mesoscale. And this one is ISM. ISM pun ada dua, user defined and also weld kinematics. Yeah. So you see, yeah, dia punya error. Yeah. And here is dia punya apa namanya accuracy. Yeah, the accuracy. So here you can see also. Yeah. Experiment is here. Yeah. TMM of course. Yeah. TMM is always the best. Yeah. You can see here. After this apa namanya this research ni, yeah, we found out that TMM is very good. Yeah, we have to use this TMM for other purpose. Which one? See you later. So this is for the WJAM with substrate. Yeah, kalau Cranfield they call it as the RUAM, ready to use additive manufacturing, together with this substrate there. Yeah, so we did also here. One interesting thing is here, the material model. Yeah, you see here material model kita ada tiga. Yeah, the first one is from the database. Yeah. The second one is for the filler materials, potong, tengok the compositions. Yeah. And also this one is from the component. Yeah, you can see here the error. Yeah, error dia. Yeah. So you see here database. Database ni tipu semua. Yeah. So bukan tipu maksud saya. You cannot use the database. Yeah, because it can deliver apa namanya not so good result. Yeah. The best is actually from the component. Yeah, the component check. Yeah. So this one is we are using the material modeling software, GMAT Pro. We see dia punya apa namanya the compositions. You can see also here the compositions. Yeah. Wire component, yeah, and also database is different. Yeah, from this we model the material, yeah, and then we check the distortion. All right. So we are using also meso scale, yeah, for this apa namanya, for this bracket. Yeah, you can see also here the apa namanya the error, yeah, 1 point something, yeah, percent. Yeah, so it means that TMM ni memang okay, yeah. So here, yeah. So after we know yet that the apa namanya the TMM is okay, then we would like to replace the calibrations yang tadi yang very tedious tadi yang kena potong and so on and so forth. Yeah. We do the calibrations by using the TMM. Here. Here. Yeah, we call it as the virtual calibration test by using the TMM. Yeah. So we do here is multi-scale, yeah, macro and meso. So here bunker, yeah, normal. Yeah. So here we compare with the experiment. That one is also the first apa namanya investigation of us. That one is from Cambridge. Yeah. So we see also the percentage error. Yeah. It is around 8%, something like that. Yeah. With the virtual calibration test. So and then we test into the component like this. Yeah. Also by using the virtual calibration test. Yeah. So we have around 5% something like that, error. Yeah. But you can compare here, yeah, the computational time for the meso scale only, yeah, 14 hours. Yeah. Here is by using the macro and meso, yeah, it's only 5 hours. Yeah. So we started also without substrate, yeah, for warm, yeah, wire arc additive manufacturing. The problem is, yeah, yang tadi sebelum ni is with the substrate, RUAM, yeah, ready to use additive manufacturing. Now, we would like to cut here, but in the software it is not available. Yeah. So kita kena buka software tu, open the software, yeah, and then modify the subroutine, yeah, so that we can have only this substrate, yeah, and then do the experiment and so on and so forth, yeah. And this one is also around 3%, yeah, for the TMM, yeah, for this kind of the research. Okay, we have done also couple process, yeah, forming and welding. This is also very interesting, yeah? And this is actually given by kita punya partner, yeah, from the Cambridge University. Yeah, we do this one. Yeah. And then okay, the interesting point is actually here. Yeah. This is actually the residual stress if you do without the forming history. Yeah. So kita buat forming dulu baru welding. Yeah. Ini without transferring the forming punya history from the previous process. If you transfer all of the geometry and the material, yeah, to the next process, here welding, yeah, before that you see here the difference, yeah? Yeah, so that you can get better result, yeah, if you take the data from the previous process. Okay, go faster lah ya. So ini pun we do for the phase transformations, ya. Also guna subroutine, ya, kita buka, open the software, ya, write the coding, ya. So that's interesting, ya, karena kita manage to do this simple subroutine actually, ya, with the model of the Seifert Kasat kit, and it's also from Rostock, I think, the professor from Germany also. Very simple one, ya, just untuk tengok dia punya apa namanya Martin-Side, ya, Martin-Side punya apa namanya predictions, ya, berapa persen we compare to the CCT diagram, ya. So we see here, the error, we get is around 10%, 15%. It's quite good. So this one is for the steel, low carbon steel. So next we try to do for the titanium pula. It's also very interesting. For those yang nak going to the phase transformation punya predictions here, please contact us. We can do it together. Grain size, we have done also, for the predictions of the grain size after war. So we did also with German punya counterpart, because we don't have the dilatometer here. We did it in Germany. Grain growth model is a lot actually, but this one we choose this one because this one is quite simple. Arrhenius equations, with exponential blah 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 blah. So and then this one is without precipitations. This one is if you have precipitations. It was very very good actually. So if you can write the coding, you can also see the grain growth punya evolutions later on. So what we choose is actually this one, because we know, in welding it's very fast. There is no precipitations. Thanks God lah. So jadi ada something yang kita remove from here, from the equations, so that one will be very simple, and then put in the algorithm coding and so on and so forth. Kena writing sikit coding so guna runga putar. I think the students they know already numerical method, runga putar, whatever they punya method, Newton-Raphson, but here is we apply this kind of the optimization method. Okay, the result is quite good. It's around 5 to 6% of the grain size. All right. Okay, for cutting we have done also. So here is also very interesting. If you do the FEM today, and you run again tomorrow, it will give you result the same. So if you do experiment today and you do experiment tomorrow, the results are different. Why it is like that? Because there is probability there. So that we need to put also the probability factor into the FEM. We call it as the probabilistic FEM. What we do here is actually we continue the research on the grain growth, also by using the first equation, without precipitation, and then we do the Monte Carlo here. Put the Monte Carlo on the power, because you see kalau welding, if you see welding, the current is fluctuate, the voltage is relatively constant. In cutting is different, the voltage pula fluctuate, the current is relatively constant, but it brings to the power, so the power is fluctuating. One of the factor that can change the process is actually the power. So here is actually the Monte Carlo method. Very simple actually. This one. Put into the coding, and then see the result. So here, if you use the probabilistic simulations, you can have still big actually, but somehow it's better than deterministic. This is our future. This is on the crystal plasticity. by using Damas free. Ya, please join us lah kalau misalnya ada yang nak ni interested on this crystal plasticity punya micro model. Ya, so we are trying to understand also this kind of the model. Yeah. Alright. So conclusions very fast. Yeah. If dealing with carbon process, transfer considerations, your geometry and so on and so forth. Yeah, it's very important. Material modeling. Yeah. I've shown database around 20%. Yeah. Feedstock around 10%. Kalau component 5%. Yeah. So you see here. Yeah. So the difference of the error. Here also for the TMM, yeah, heat transfer coefficients. Yeah, if you choose the default, yeah, in the data in the software, yeah, normally they put here 1,000, yeah, here 20, yeah, but it's wrong. Yeah, we have done the investigations, yeah, and then proof, yeah, and then put this new one, yeah, new value, yeah, we got the better result. Yeah, combinations, multi-scale, yeah, TM, MISM, yeah, macro, meso, or meso, micro, yeah, it's becoming trend, yeah, on that. Okay, probabilistic FEM, yeah. Lumping method, yeah, can save the pre-processing, yeah, and also compositional time, yeah. And then couple this one, yeah, meso, micro, and so on and so forth, yeah. So this is also becoming the trend for that. Successful presentation need here, yeah, collaborations. Yeah, that's why. Yeah, we need also the collaborations here. Yeah, we don't have also all of the equipments we need. Yeah. So here for the academicians, yeah, lecturer and so on and so forth. Yeah, this factor, yeah, numerical method, yeah, material, technology parameter, the design, yeah, and coding. Yeah, so it's important. So if you would like to find the postgraduate, good postgraduate students yang nak buat benda-benda macam ni, kena tahu juga coding. Okay. So for the research kita, yeah, fluid 3D, yeah, is combinations between TMN and CFD. Yeah, on that, this one is the cage valve. Kita buat pakai FDM. Dia try tengok dia punya ni. Objective is the pressure drop, minimum pressure drop, and target volume. This is valve. Yeah. This is our dream actually. Yeah. Nak buat valve without any regulator here. Yeah. Just simple one. Yeah. By using the fluid chilling. Ini yang baru. Yeah. Ultra lightweight component with lattice structure. Yeah. Here, yeah, GD plus lattice, yeah, plus material yang high strength, yeah, titanium 64. Yeah. So we would like also to do the simulations on the tensile test or full test here. Yeah, see the damage and so on and so forth. Here from the Queensland, yeah, they find out gyroid is the best punya lattice structure. Yeah, we try also to simulate, yeah, but still far away from this one. Tapi somehow dia punya ni is okay. Somehow dia punya result is the trend is need to be improved. This is crystal plasticity. So crystal plasticity, yeah, meso and micro, yeah, combined together. Yeah. For what is this? Yeah, this one to investigate the number of cycle to initiate a short crack. Yeah. If you see here is the experiment. Yeah. This is the cycle to initiate. Yeah, by using the Tanakamura here. Yeah. So Tanakamura model, also TMM. Jangan salah. TMM, this one is Tanakamura. Nak tengok the number of cycle. This one is by using micropillar. This one we did it in Slovakia, not in Germany. Yeah, but in Slovakia they have this micropillar. They call it, yeah, micropillar like this. Compressed to find the CSSR, critical stress resolve stress. So 134.5 MPa. This one is P91. Yeah, you see here yield is 550. 690 is UTS. You see here. This one is our cracking criteria. Yeah, the shear stress must be 2 times of the CSSR. So the CSSR is obtained from this one, micropillar. Yeah, this last slide. Okay, this one is a general method. We have tried to have the method. For this one is for WJAM. We call it the 11 steps for high quality product of MAM. From the design. With the inclusions of the simulations. So here is the simulations part. It's done here. And also here for the SLM. So our task is actually to combine these two together, so that we can get the simplified methods for the metal additive manufacturing. I think with this, so I end my presentations. Thank you very much.
Thank you, Prof. Peter, for the amazing sharing session. So we would like to open a Q&A session. If there are any questions.
Yes, thank you, Prof. My name is Rashdan from Unit 10. I would like to ask about the residual stress evaluation just now. You put the two different situations, right? Where you transfer the geometry and without transfer the geometry, right? Just to ask you how to transfer the geometry actually. Is it we have to perform two stages of simulation, or we simply import the data from the experimental work?
We have to do the first simulation first. So in this case, we are doing. We have done the forming and welding. We have done the forming first. And then the results, including the geometry. Because this one is deformed. Transfer to the welding simulations. So the software must be compatible to each other.
Example for software is like the one that you mentioned just now.
Simulfect.
Simulfect.
I'm not the seller.
Okay. So is it okay if I have another question, Prof?
Yeah.
About the grain size. So how actually do we determine the grain size using the FDM? Because grain size is not the same as the mesh size, right? Is it the same? No. So how do we determine actually? Just do the experimental work.
Yes, it's actually by having the contour plot. So and then this contour plot is produced by the model, the grain growth model we use here. We write the subroutine. So that the result will be displayed in the contour plot. Not the meshing. So jadi the contour plot too will indicate the size.
Understand. Right.
We cannot get the picture, No, cannot get.
Okay. Based on the numbers.
Based on numbers.
Is there any more question?
Sorry, ada drag sikit organizer. Sorry.
Okay, thank you. I think there is no question. Thank you, Prof. Peter, for this session. So next, we would like to have a photo session at the front. So please come to the front. Maybe some can stand on the stage. Some can on the floor.
Baru. Boleh. Sudah. Pak Ibu. Pak Ibu.
Ya.
Baik bos.
Ya.
Okey. Okey, dah alhamdulillah.
Ini balik ke sini ke kami. Ftwjam. Dah habis kan? Habis sini. Di sini. Itu jatuh tu.
Thank you everyone. Now we have tea